I'm Valerie Butler, and I'm with Environmental Management at Kirtland Air Force Base in Albuquerque, New Mexico. The Trestle is the largest horizontal electromagnetic pulse in-flight simulator to be created in the world. The Trestle project is one of many programs that played a significant role in our nation's military and strategic security interests. Through the National Historic Preservation Act of 1966, Section 110, an inventory of facilities at Kirtland Air Force Base was completed, and the Trestle is determined eligible to the National Register of Historic Places. Therefore, Kirtland Air Force Base decided to document its integrity by completing a historic American engineering record.
Traditionally, we would use tape measures and plumb bobs and try to measure things to a 1/4 inch of accuracy. But I just couldn't imagine actually doing that with this structure. I couldn't believe how large this structure was. And previously I'd been talking with laser geomatics about using laser scanning for some of the work we do. So immediately I thought, let's do that. We'll increase the precision on the project, also get a 3D model out of it, and have this amazing structure documented that way.
As part of the Trestle documentation, Van Sitter's Historic Preservation asked us to help them create 2-dimensional historic American engineering record drawings, as well as a 3-dimensional model of the Trestle site. We scan the Trestle with LiDAR technology that we call the HDS 2500, which is a line-of-sight, time-of-flight scanner. During field operations, which took approximately 8 days, we collected 88 separate scans, or about 37 million points. As well as Bohannon Houston surveyors collected state plane coordinate information of those same areas that we scanned to bring it into the actual site of the Kirtland Air Force Base. After we finished the field operations, we bring the information back to the office and stitch or register the separate point clouds into a composite database or a 3-dimensional view with all of the points in one view. From that, we create, as we did in this project, a 3-dimensional model of objects that we can use to not only create a 3-dimensional fly-through or animation, but also 2-dimensional historic American engineering record documents.
So once the laser scanning team got started, I got my historical team involved in doing the documentation of the Trestle. And to do that, we went through a lot of archival research. We spent months looking through daily, weekly, and monthly reports. We found old oral histories, we found old video, any information we could find, correspondence, anything we could find, we gathered and pulled together and then sifted through it to develop the actual written history of Trestle. And through the process, I've met many amazing people and had one of the most rewarding experiences of my career.
It is due to this process that we are able to bring you the landmark of the Cold War Trestle.
The Cold War, as journalist Walter Lippmann first coined it, continued from the end of World War II in 1945 to 1989, when the fall of the Berlin Wall symbolized the end of the conflict. During the time of hostility between Eastern and Western Bloc countries, the United States conducted underground and atmospheric tests, as well as simulations, in order to maintain nuclear superiority over the Soviet Union.
The Cold War was a period of considerable anxiety, anxiety that stemmed in many ways from a combination of fear of an adversary that everybody knew was out there, the Soviet Union, but also anxiety that stemmed from a considerable amount of uncertainty over precisely what was going on in the world and the global environment. Americans, of course, knew that nuclear war would be a horrible thing. It would be terribly destructive and dangerous. But the precise details of it were something that were not really available to them. How many weapons were we talking about? What were the targets? What would the effects of those weapons be? Under what circumstances might a nation actually use nuclear weapons? All of those things were unavailable to the public because at the time, of course, they were secret. And the fact that they didn't know a lot of those details also made it all the more frightening and raised the level of anxiety. Within the nuclear weapons complex, I think, of course, those people had more information about the precise details of nuclear weapons and the possibilities of nuclear war, but they were nevertheless still anxious and uncertain about other matters regarding the competition with the Soviet Union. In particular, they wanted to be very careful to avoid what historians refer to as technological surprise, right? The fear that some new technology or application could sort of come out of the blue and upset what was regarded as a delicate balance between the United States and the Soviet Union, and provide one side with a considerable advantage, right? The last thing you wanted to have happen was for some new technology to come along and catch you unawares or unprepared. And so throughout this period, there was an enormous imperative to explore all of the military technological possibilities that almost anybody could think of, not only because they might be useful militarily for the United States, but also to try to avoid being surprised by the Soviet Union.
It was during open-air nuclear testing that the United States military discovered a destructive byproduct of high-altitude nuclear explosions, bursts. This discovery was electromagnetic pulse. Electromagnetic pulse, or EMP, is detrimental to electronics and develops when gamma rays from a nuclear explosion interact with the atmosphere. The gamma rays ionize an area of the atmosphere and produce an electric field. EMP currents can reach their peak at faster than 10 nanoseconds and are so incredibly powerful that they can spread at the speed of light. In a high-altitude nuclear burst, electromagnetic pulse extends in all directions on the horizon, affecting metallic conductors, including antennas, cables, conduits, power lines, aircraft, and missile bodies. The pulsed conductors then feed the energy into electrical and electronic equipment, burning it out or damaging it. Equipment that operates at low currents, such as computers and solid-state systems that are semiconductor-reliant, would not withstand an EMP power surge. This could result in malfunction of aircraft and other military equipment.
It was very important to understand the interaction of this with such systems, because if some class of strategic system had a fault, it's possible that from a high-altitude EMP burst, which can put fields over the entire continent if you do it just right, that you could have some Achilles heel. And so we had to understand this so that that couldn't happen. This was particularly important on the strategic equipment, not so much the tactical equipment. And we had to not only solve this problem, but convince the former Soviet Union that in fact we had, so that we were not vulnerable to such an attack.
The first recorded electromagnetic pulse incident occurred during a high-altitude nuclear test in the Marshall Islands. During this detonation, called Starfish Prime, a 1.4 megaton test blast detonated over Johnston Island at an altitude of 248 miles. This detonation resulted in electronic system failure felt as far as Hawaii, more than 800 miles away. Street lights and fuses failed on the island of Oahu, and telephone service was disrupted on the island of Kauai. Owing to this test, it was discovered that if a nuclear detonation took place 200 miles above southern Canada, the EMP effects would cover nearly the entire United States, potentially incapacitating electronics throughout the country. Late in 1958, both the United States and the Soviet Union voluntarily suspended nuclear weapons testing. In reaction to a detonation of a nuclear device launched by the Soviets in 1961, the United States made the decision to resume testing and continued until the signing of the Limited Nuclear Test Ban Treaty in 1963. Although the Limited Nuclear Test Ban Treaty ended nuclear weapons tests or any other nuclear explosion in the atmosphere, outer space, or underwater, underground testing was still permitted. In light of the atmospheric test ban and the continued threat of the Cold War, the United States began to look to simulation methods to determine the effects of nuclear blasts on military material. Two types of EMP simulation tests were to be created and executed at Kirtland Air Force Base under the direction of the Air Force Special Weapons Center. One test would determine the hardness or functionability of equipment after receiving an electromagnetic pulse, and the other would explore specifically the effects of EMP. Once this information was gained, the Air Force would take measures to harden or protect military equipment so that it could function should it come in contact with electromagnetic pulse as a result of a nuclear detonation. During the Cold War, more than 18 EMP simulators were built and utilized in the United States. Many of them were located at Kirtland Air Force Base. These simulators were used to test cruise missiles, aircraft, and other military defense equipment. Although different types of on-ground simulators were already being used for testing, a simulator which tested in-flight EMP had yet to be created. At that time, it was considered critical to have information on how aircraft would respond when struck by EMP while flying.
We used the testing to verify that the EMP hardening which had been put onto the aircraft was in fact holding up according to specifications. And in almost all cases it was. The few cases where we did find some deviations and needed extra hardening, this was reported to the project office and to the manufacturer so that they could increase the hardening. This was to guarantee that our aircraft could withstand an EMP during a nuclear attack and continue operating in order to defend the United States against the Soviet Union.
In April of 1969, a member of the Air Force Weapons Laboratory's technical staff, Captain Carl Baum, began to look for a way to prove various mathematical models regarding the coupling mechanism between electromagnetic pulse and the inner workings on the aircraft while in flight. Somehow, it would have to be determined whether or not aircraft would survive EMP while flying. To do this, an in-flight electromagnetic pulse simulator would need to be created.
If equipment is sitting on the ground, whether it's a parked aircraft, an automobile, whatever, a tank, the thing we're concerned about is the high altitude EMP coming down from space basically, incident on the ground, but there is a reflected wave coming up from the ground. The environment to which the system is subject is those two waves, not one wave, and its close proximity to the ground actually affects its response, or as we might call its Green's function. For an in-flight configuration, we have essentially one wave coming by because the reflection from the ground comes by much later in time and can be considered a separate event. We already had simulators for both things on the ground and for small in-flight systems like missiles and small fighter aircraft. We needed something for large strategic aircraft, bombers, flying command posts, things like that. And we didn't have such a thing, and that's what led to the design of this simulator.
During 1973, as design and construction moved forward for EMP simulation testing facilities, the Air Force Weapons Laboratory issued a solicitation for 3 contractors to produce proposals to develop an in-flight simulator. The 3 companies were McDonnell Douglas, Boeing, and General Dynamics. In April of 1973, McDonnell Douglas was awarded the contract. To resolve the problem of developing a large in-flight testing facility that could support an aircraft, pulsars, and equipment, Dr. Baum suggested the use of a dielectric structure which would support the aircraft well above the ground and avoid electromagnetic coupling between the system being tested and the ground.
The basic problem was to get a large, heavy aircraft away from the ground, to allow a horizontally polarized electric field to be incident upon it, and to avoid the problem of the interaction of the aircraft resonances with the ground. This was a very difficult problem. People were thinking, should we jack the aircraft up in the air? And we're thinking something very large like a Boeing 747, which is much more difficult than a fighter aircraft. In 1969, I wrote the paper which sort of defined the concept of how to do this a different way, in this paper right here. And what it was remembering some of the old movies about how the Union Pacific Railroad was built coming through the Rocky Mountains from the west. You would tunnel through the mountain, or you would build a large wooden trestle across the canyons that a train would actually drive across. And so I reasoned, if you can drive a train across a canyon, I guess you can drive an airplane across a canyon.
The largest horizontal in-flight electromagnetic pulse simulator ever built is the Air Force Weapons Laboratory Transmission Line Aircraft Simulator, or ATLAS. It is commonly known as Trestle because the ramp and test stand have a railroad-like appearance. In order to properly test large aircraft in simulated flight mode, and so as not to create interactivity with electromagnetic pulse, the test stand was created using wood, which is dielectric material. It does not conduct electricity.
Well, for our company, we had done many large projects in our time, and this, of course, was a large project, and of a magnitude that, because of its nature, we had never done this type of project before.
Wood systems of the trestle are really unique and are enormously unique. Having gone out there this morning and taken a look at what had happened in the intervening 31 years is kind of interesting. And you know, there are 6.5 million board feet in the thing, and of glue laminated material, and there are 10,000 connections in the structure. They have split ring connectors and the gusset material. And some of those members, as I think that we were looking at some members that were 54 inches deep by 14 inches wide. They had to bring them in on 3 rail cars.
To create a simulated flight environment at Trestle, the aircraft needed to be placed on a platform constructed above the ground and of a non-conducting, non-reflective material so that the simulated test would see it as air. Horizontal transmission lines were supported high above the ground. With this configuration, the aircraft could be tested in its normal upright position with the incident electrical field parallel to the largest dimensions of the aircraft, the body, or wings. Trestle was intended to support the test program with in-flight capabilities and provide an environment with considerably fewer testing limitations than previous simulators. 2 main concepts were considered for the large horizontal in-flight EMP simulator. One option included the torus concept, a huge circular or arched structure extending around and over the earthen bowl created for the trestle structure and held up by a balloon and tethered with cables. In this conceptual design, a high-voltage pulsar was located along the arch of the torus. Although this design had several advantages, including wide variability of angle of incidence and polarization and unimpeded access to the simulator working volume, the disadvantages outweighed these advantages. The complexity of the operation because of balloon handling, as well as the requirements for very high-voltage pulsars, made this design less feasible, especially with the threat of high winds. The second option was a guided wave simulator that used a large transmission line driven by a high-voltage pulsar. This included a conical transmission line extending across a large earth depression with pulsars at one end and a trestle platform extending from the other end into the transmission line. The major advantage of the transmission line simulator was that an appreciable fraction of the total energy output of the pulsars was channeled in a preferred direction, so that higher field strength could be obtained in the working volume with less energetic pulsars. The pulsars required to operate such a system were thought to be available at the time. However, the system could not provide the versatility in polarization and propagation direction that the torus design could.
Well, the mechanical engineers were mostly concerned about this large wooden trestle. It was a very significant mechanical engineering problem. But its function is to be a test stand to hold the aircraft up. It is not part of the simulator. Its function is really to be invisible to the electromagnetic wave, at least approximately. The simulator itself is the pulsars, the guiding structure or transmission line, and the terminating resistors at the end. That's the simulator, not the trestle.
As I recall, when I joined Trestle, it was in like September of 1973, and the final design had not been ironed out yet. Our integrating contractor, McDonnell Douglas, MacDac as we called them, they were advocating a glued module design that kind of stacked modules, one on top of the other. And we did not care for that design because it was not traditional enough in terms of we needed buildability, constructability. We needed something that was the industry was used to.
The final wooden trestle design was constructed well above grade with a pulse-producing system that would create an electromagnetic wave. The wood selected for construction was glue-laminated western larch and Douglas fir, or glue lamb. The structure was built in an arroyo, an area where the ground naturally drops off. The area was then graded to create a bowl.
The wood, more specifically the glue laminated wood, allowed us to achieve more homogeneity with the structure than if we would just work with the rough sawn or finished four-side material that was not glue lam, because what we could do is engineer the certain properties into the members that we could use to carry the loads.
And so the basic idea was not to get the plane away from the ground, get the ground away from the plane. And so you moved out to a location where the ground naturally had that contour, required very little earth moving by comparison, and you drove it out on this trestle, the ground having been removed by nature for the most part.
Building the structure across the arroyo bowl, which ran from north to south, allowed a towing ramp for the aircraft to be moved into position on the test stand. Transmission lines surrounded the trestle platform and carried electromagnetic pulse from the pulsars located on either side of the central ground plane wedge to the terminator located at the north end of the ramp. The central ground plane wedge, located at the south end of the structure, held the shielded control room and offices. The wire mesh-covered steel structure rising from the building served as a portion of the transmission line. The wedge was the control center for trestle operations. It had 4 levels, each served by an elevator and 2 outside stairways. The first and second levels are enclosed to provide habitable office space, storage, and work areas. The third and fourth levels are semi-protected from both the weather and semi-electric field environments. The fourth level was called the pulsar level, and personnel were excluded from this level in the area immediately adjacent to the 2 pulsars during firing operations. The idea was to fire the pulsars at the same time, generating an EMP wave guided by the transmission lines onto the test stand and into the aircraft being tested. The test stand was designed as a 200-foot square, but in order to reduce construction costs, a 30 by 30-foot square that did not affect the turning radius of the aircraft to be tested was removed from each corner of the structure. The ramp and test stand are separate structures in that they are not pinned or fixed to each other. These are the measurements of the trestle. The width from the bowl, rim to rim, is 600 feet, which is the length of 2 football fields. The bowl itself is 120 feet deep. The transmission tower is 185 feet tall with 68 feet of glue-laminated wood. The wedge length is 250 feet long and 240 feet high. The ramp is 50 feet by 400 feet and 12 feet up to 115 feet high. The 2 pulsar supports are 30 feet by 70 feet by 74 feet high. The tower power poles are 26 inches by 26 inches by 68 feet high. There are 6.4 million board feet of glue-laminated wood. There are 12,000 square feet of gusset plates, 10,000 joints, 60,000 dielectric bolts, and 120,000 split rings and shear plates. The length from wedge to terminator is 1,300 feet, or 4 football fields. The Trestle is the largest EMP simulator and wooden structure in the world. According to William Shover, the original Trestle budget was $25.4 million. The final cost of Trestle totaled almost $60 million. Bob Krause was the structural engineer who designed Trestle. The structural design was completed by R.D. Krause Engineering in Santa Fe, New Mexico, and W.C. Kruger and Associates in Albuquerque, New Mexico, under a subcontract with McDonnell Douglas Aircraft Company. Originally, Trestle was to be composed of individual wood truss columns. The final design was more of a standard trestle bent, with braces interconnecting the structure throughout. The bent structure was designed to withstand a wind load capacity of 40 miles per hour with an aircraft sitting on the test stand. Trestle alone could withstand a wind load capacity of up to 100 miles per hour.
I knew that this was a gigantic structure, and it was really involved, and that everything that we did, we would have to think big, because everything was big in size and quantity in putting this project together. Being a structural engineer on the project required research in every phase of engineering. A lot of it was very basic and new. Research such as the wood species going into the glue lams, to the laminated gussets, bolts, and so forth.
The deck for the test stand and ramp were originally designed using a corrugated method. Ultimately, both structures were constructed of glue-laminated wooden beams. The deck planks are 37.5 inches by 15 inches by 52 feet long, consisting of 4 edge laminations. They were manufactured with an edge gap tolerance of no more than 1/4 of an inch. Woodlam Incorporated of Tacoma, Washington, fabricated the beams, which were then inspected. The treated glue-laminated members were shipped by rail directly to the construction site. The beams were so big it took 3 railway cars to get them to the site. Weighing 20 tons each, the beams had a cross-section measuring 40.5 inches by 31.5 inches, and each incorporates 20,000 board feet of Douglas fir and western larch lumber. 2 large cranes lifted the beams off the railway cars and loaded them onto a segmented truck bed to move them into place for construction. The Air Force determined that bolts should be used for the joint connectors of the trestle. Engineers began to evaluate how these connections should be made. A method was developed using split ring connectors and dielectric bolts. Split ring connectors are ring-shaped metal inserts that collect the load from one timber member and transfer it to another. A ring is split so that it can be fitted into a circular groove on the meeting face of each timber. The groove is slightly larger in diameter than the split ring, and the split of the ring opens when the ring is sprung into the groove. The gap that is created at the split may open or close as the wood expands and contracts based on its moisture content. This ensures that the metal ring and wood are always in contact. Some of the bolts were 70 inches long and the diameter of a broom handle. The undertaking of the construction of the trestle was as large as the structure itself. The specification timeline for use of this facility was set at least 10 years. The original initial operating capability dates were to be July and November of 1975, respectively, to accommodate a simulated in-flight testing of the E-4, known as the National Emergency Airborne Command Post, or Flying White House. The Defense Systems Acquisition Review Council 3 used the E-4 tests to plan their decision about production. Although the facility was designed to test the E-4, the aircraft was never actually tested at Trestle. Simulation testing began in 1980 with the testing of the B-52. The Trestle development program included military and civilian staff members as well as consultants to support the engineering analysis for the design of Trestle and review of the work completed by McDonnell Douglas Aircraft and its design consultants. The primary subcontractors under the McDonnell Douglas Aircraft contract were Maxwell Laboratories for pulsar design and construction, Braddock, Dunn & McDonald for electromagnetic analysis, timing, and control equipment, W.C. Kruger & Associates for mechanical and engineering design, R.D. Krauss Engineering Company for structural engineering. At the end of the McDonnell Douglas contract, the Allen Campbell Company was hired to construct the wood test stand and ramp.
And there were countless structural engineering firms in New Mexico and throughout the United States that was capable of doing this work probably better than I could. But since I snuck in piggyback on W.C. Kruger, I was happy to have the job. And during the design of the project, I probably employed 5 or 6 of my people full-time. I only had a total of 13 people in the firm.
In total, more than 39 different companies provided consulting, labor, or materials to help create Trestle.
I didn't do it all by myself. I couldn't have. I worked with the finest bunch of engineers and scientists you could want to work with, and they were dedicated to the Trestle to make it a reality. Most notably, I'd like to mention that Bob Slater, Ted Morelli, John Unvarsky, Bob Rocker, Doug Merkel, and our consultants Doug Stadelman, Don Neal, and Wilbur Birchler, and others, that I really should commit them to this history because they really made it happen. And I wish I could remember everybody, but I can't do that. In the final analysis, the Trestle project was just incidental to my association with people like Bob and Ted and the others. We had a tiger by the tail, but it was fun. And I think I got more out of the Trestle project than I gave to the Trestle. I guess the structure as it stands out there is just a tangible testament to our collective gifts and abilities.
That's great. It took 7 years from the groundbreaking in 1973 to the first test of a B-52 aircraft in 1980 using the EMP test simulator called Trestle. Before testing could take place, safety procedures were developed and a fire protection system was installed. The wooden structure could burn for 4 hours before it would lose any of the structural integrity.
You see this white plastic pipe down here?
Uh-huh.
It's empty, okay?
Yeah.
Except you see that big water tank over there?
Uh-huh.
When you flush that, water rushes down through this pipe here, and then it subdivides. You see some of the other smaller plastic pipes here, fiberglass? It distributes the water around this whole thing and it comes out those sprinkler heads.
The planned fire protection equipment was installed at Trestle prior to testing any aircraft to reduce risk to aircraft and personnel. The minimum quantity of water for the system was 8,000 gallons per minute for a period of 1 hour, which required a storage tank of 500,000 gallons. The average fire hydrant pumps around 1,000 gallons per minute. In order to ensure human safety, the Air Force Weapons Lab developed safety procedures specific to the EMP facilities to ensure personnel would not be harmed by EMP testing. Civilian personnel were excluded from areas in which exposure exceeded 50 kilovolts per meter. Military personnel exposure was not supposed to exceed 100 kilovolts per meter. It had been shown that relatively low EMP field levels could cause cardiac pacemakers to malfunction, although the effect was less severe during single pulse than repetitive pulse operations. No injuries resulting in death occurred either in the building or testing of the Trestle.
The most dangerous part of the operations was the handling of the aircraft. When we were moving the aircraft and when we were running engines on the aircraft. And at that time we had a full-time safety officer and all the employees were briefed on safety procedures. And we had an Air Force crew standing by who was used to handling the aircraft and would place the employees when we were running engines and keep everyone out of the way when we were running engines. We always had a fire truck standing by anytime we had engines running in case there was a fire, which there never was. We never had to use them.
Once the aircraft was on the test stand, EMP simulation at Trestle was produced by rapidly switching a high-voltage, high-energy pulse from the pulsars onto the transmission lines. A warning sounded and flashing lights were set into motion prior to the initiation of the test. The Marks generators were charged for 2 minutes, and on command the pulsar discharged into the transmission line. The antenna then radiated an electromagnetic wave in a similar manner to a radio wave. The pulses created during a test were of nanosecond duration, and although there were millions of volts, the pulse itself did not have a visual characteristic. There were no flashes, blasts, or shocks, but there was a small sound due to the discharge from the main output switches, similar to the sound of a muffled .22 caliber rifle. The greatest effect that could be noticed was a click on an audio circuit. Aircraft test programs at Trestle ranged from 3 to 6 months, with a standard 5-day work week and second shifts as required. During times when no testing was taking place, there were 25 administrative crew members at Trestle. Approximately 50 additional personnel arrived on site to conduct the tests and worked from trailers. To begin a test, the aircraft was instrumented at specified locations to monitor the electrical response. It was then towed along the ramp to the test stand and was positioned in the orientation required for the test. Test orientations included moving the pulse across the aircraft from nose to tail to nose, wingtip to wingtip, or at an angle in between. Once the aircraft was in the testing volume with the proper test orientation, the final monitoring instrumentation was added. In the first checkout test on March 1, 1980, a B-52 was towed onto the ramp and into the testing position. An electromagnetic pulse struck the B-52 as a wave and entered through the communication antenna, cockpit windows, ground access doors, as well as diffusing through the ecking. The solid-state devices that were not hardened against electromagnetic pulse were burned out, or their operation was upset by interference with computer memory and navigational aids. The following aircraft were tested using the Trestle horizontal electromagnetic pulse simulator: the B-52, the B-1, and the Takamo.
The main aircraft that we were trying to test for EMP hardness was the heavy bombers and the cruise missile carriers, because this was our primary defense against the Soviet threat. We also tested helicopters, including the President's helicopter, as well as fighter aircraft such as the F-16, the F-14, the F-18, and other Navy aircraft.
At the end of the Cold War, the Air Force Weapons Laboratory requested a plan to maintain the Trestle simulator in inactive status, with the idea of potentially reactivating testing. However, there were significant impacts in keeping the Trestle dormant at baseline operability. Deterioration from lack of maintenance. It took as many as 6 employees just to maintain the Trestle wood systems. Increased test startup time. Increased cost to ready the facility for testing. Increased equipment failures. Conducting a new wood study analysis to ensure safety. Loss of personnel with Trestle expertise requiring extensive training of new hires. Lowered pulsar reliability. Lowered rates of data acquisition. Ultimately, the decision was made to discontinue maintenance of the Trestle simulator and other simulators around the nation. The Trestle would be allowed to deteriorate without further maintenance or repair.
The last test on the Trestle of a strategic bomber was the B-1, which was tested in 1989. After that time, we were still maintaining the Trestle platform in anticipation of the next strategic aircraft that was to be tested in the early 90s, which was the B-2 stealth bomber. However, with the fall of the Soviet Union, the DoD de-emphasized any further nuclear testing of any kind, and the funding that was supporting the maintenance of the Trestle and the Trestle platform was reallocated somewhere else, and for us the money went away. Since 1994, the Trestle platform has not been maintained.
I point out that the Atlas I and other EMP simulators, this just being the biggest one ever, were a vital part of the Cold War. They provided us with vital information for protecting our strategic systems. Equally important, they demonstrated to the world, and the Soviet Union in particular, that the United States was seriously addressing the EMP problem. Now, with the end of the Cold War, these are in disuse.
The date of the last EMP simulation test was 1988, and the Trestle has not been used since 1990. Thus, the Air Force began historical documentation in order to record the importance of the Trestle and its significance during the Cold War.
The EMP Trestle, I mean, it's an interesting story. It's one of those somewhat lower key stories in a way in nuclear weapons research in general, right? When we think of nuclear weapons tests, we think of the large mushroom clouds and the tests out in the Pacific or at the Nevada test site and these huge explosions. And here was this somewhat more exotic effect that was identified early on, but not really explored until much later in the Cold War period during the 1970s.
Later in 2002, I had the opportunity to visit Kharkov, Ukraine, part of the former Soviet Union. There is where they actually developed the EMP simulators and shipped them to other parts of the Soviet Union. They showed me through their facilities and showed me the papers, my papers, and we had some serious discussions, and we felt at this time it was really the end of the EMP Cold War, and we're all friends now.
Simulators like the Trestle gave the United States scientific challenge and valuable information, resulting in the improvement of military aircraft and equipment.